Yeah, thank you very much, and thanks for having me. It's a great opportunity to talk here, and I again thank ICTS Dynamics of Complex Systems on arranging this kind of a thing for a summer school. And when it comes to GFD, I think an important thing is that we have a very small community in India, and what my talk will focus is on how, as I am completely a mechanical engineer by training, but I'm pretty well doing GFD. My bread and butter comes from that. But so one can actually do GFD from not having a GFD background. So this is what my talk will be on. It is basically on classical fluid mechanics and its relation with classical mechanics, and how it is applicable to GFD, and some aspects of applied maths, which actually is the entire thing about GFD itself. So it's on the connection between wave resonance, shear instability, and oscillator synchronization. And I acknowledge some of my collaborators and my funding agencies. So it is mostly about a paper I wrote while I was a PhD student. It's a part of my PhD work in JFM. So I know that you have gone, the students here have gone through an introduction to instability, and probably Professor Rama Govindarajan has gone through it, but I just wanted to have a picture is what is meant by stable. As you know, if there is something of this kind of a shape, this ball will roll and it has a tendency to move towards the equilibrium, and that's kind of a marginal stability, and it will kind of oscillate, or if it is on the hill, it will just move downwards. And so this corresponds to, if it is a pendulum, it corresponds to the stable equilibrium, and the unstable equilibrium if it is an inverted pendulum. So it is a classical problem which people have done, and then the analog to it in fluid mechanics, as if you are a mechanical engineer or civil engineer, you have definitely done this kind of an experiment in the lab in second year or something. Like it is a classic Reynolds experiment. You have a pipe, you put fluid, this is the dye, and the dye will show some wavy patterns, and then it will be a mess. And this is the turbulence. But the interesting thing which I'll be talking about today is as you keep on increasing the Reynolds number, you see these kinds of changes. So I'll be talking about the transitional flow or the instability regime, and that kind of corresponds to what you see about the instability itself, which I was talking about the pendulum and stuff. So what about instabilities in geophysics? So in the clouds, you see these kinds of nice structures. These are called Kelvin-Helmholtz instability. You see the same thing. This is deep inside the ocean. It is saline water. This is less saline water, and at the interface, you see these kinds of billows forming. Okay, and again, the ocean wave breaking can also be related to a shear instability. Probably more complicated is some other issues. And this is a vortex street, von Karman Street, behind an island off the coast of California, I think. And you see this nice kind of a vortex street. So these are all aspects of shear instabilities, but in geophysical setting. You obviously get shear instabilities even in engineering problems, but the same thing, but the numbers change, and that's it. But it is the same setting and same problem in fluid mechanics in a sense. So just be a little pedagogical. The traditional approach to stratified shear instability theory. So what is stratified? I mean density stratified. So as a geophysicist, so I have the coordinates here. We will be very unhappy if the coordinate here is y. We always take it as z. This is x, and no more questions asked about it. Okay, and by stratification we mean the density varies along z. Okay, so that is the meaning of stratification. Because you know the oceans or the atmosphere are all density stratified, and I'm looking at 2D flows, 3D is too complex, incompressible, because that makes sense mostly in oceans, not that much in atmosphere, but it is not that bad. Okay, inviscid, Reynolds number in oceans and atmosphere are pretty high. This is not a bad approximation in many cases. And Boussinesq, it means that you throw away the fast waves. Like Boussinesq approximation means you are throwing away very fast moving waves like sound waves in air or water, but you keep the slower waves like the internal gravity waves. So that is the main essence of Boussinesq approximation. People will say that you do not keep the density variation in the inertia, and you keep the density variation when it is multiplied by g, but that is mathematical. Like if you want to make sense out of it, it is basically this. It is a filtering process. And the fluid is also assumed to be non-diffusive. So as you know, if it is a salt stratified or temperature stratified flow, the stratifying agent does not diffuse. So the density is conserved as the parcel moves around. Now you take a mean flow that is parallel to the x-axis. So the mean flow is u, and u is a function of z. Okay. You just decompose into a mean and a perturbation. And furthermore, if you assume a hydrostatic background, which is also not a bad approximation in geophysical flows, what you get is, so you do all those approximations, and then you simply define a stream function, and you already know how to cross differentiate the x momentum and z momentum equation to get a vorticity equation. So this is vorticity. It is basically a Laplacian of stream function. I just didn't want to write more variables. So you get one equation, but you have psi as the unknown and rho prime, which is the density perturbation, but you have an equation for density also. So you have two equations, two unknowns. You just define J as a bulk Richardson number. It is a measure of strength of stratification, density stratification with respect to shear. This is very standard way of doing it. And then you write the stream function as some mean stream function and some perturbation. And now comes the instability part. Now you have the equations. Now you put something called the normal mode ansatz. So normal modes mean, so this is, you put fluctuations of this form, which basically, if you expand, so this phi or whatever psi is it, and rho hat, these can be complex numbers, and this c is also a complex number. So what is a normal mode? A normal mode physically will mean that, so what I'm trying to do, I have a mean flow, I have a base flow. I add perturbations to the flow. Okay, what happens next? What I'm looking for? I'm looking for normal mode type instabilities, I'm looking for perturbations that do not deform. It just grows exponentially, means the wave will just get magnified or like its amplitude will just exponentially grow or decay. Or if the wave is moving, its speed, phase speed or celerity, whatever you call it, that does not change. So that is kind of a normal mode. A normal mode won't get deformed. And that's what actually mathematically it comes out to be. If there is a growth, if you expand it, the growth is this. So if Ci is positive, the thing will keep on growing with time, exponentially. And this is a wave-like perturbation. So this is the wave that, just simply the wave equation that is moving. So this is a very, the exponentially growth, if positive, if everything is fine, you play this game, and what you get is, on substituting it in this equation and using the density equation, these two equations, you get the standard, this is called the Taylor-Goldstein equation, an eigenvalue problem. And probably if you have, I do not know whether Rama has gone through this thing called the Rayleigh equation or the Orr-Sommerfeld equation, but if you have gone through the Rayleigh equation is exactly this, except that when J equals to 0. And the Orr-Sommerfeld equation, you have viscous terms. If you have viscosity 0, you get the same thing when there is a density stratification. So it is a quick review of maybe of a hydrodynamic stability. If you go through a textbook, you will get that. Okay. Now, if you solve this equation, so why you are solving this equation is important. So in nature, maybe you will be given, so assume that this is an ocean, and you have this velocity field and you have this density field. Okay. You substitute this velocity u here, and this density, mean density here. Okay. And you solve it. What you get, and so what you get are which modes are unstable. So what you are doing is you are putting different wavelengths. So you are perturbing the flow with waves, all kinds of waves. It could be waves of different wave numbers. You are perturbing the flow. Now you are asking the question which waves would grow and which waves won't. And that actually comes from this equation, from this eigenvalue problem. When Ci is not zero, is this white region, these are the wave numbers where you will get growth. And maximum growth somewhere occurs for this case, somewhere here, for that value of j, the non-dimensional number, which is very important here, right? So for this particular case, which I have shown, this is the if you are simulating that, this is what happens at t equals to 0, and as time progresses, this shear layer will roll up, give rise to Kelvin-Helmholtz instability, the classic Kelvin-Helmholtz instability. It will break down into turbulence, it will become turbulence, and then it can relaminarize. So that happens as time progresses. So this is what you get from normal mode stability theory. And normal mode stability theory gives only at it's a linear theory. So it is exactly at time, it's at infinitesimally instant after you perturb it, it gives the growth rate and everything, but it is not a nonlinear theory, so it cannot predict what should be the shape of that. It just gives you what should be the instantaneous growth rate at the beginning. That's what the normal mode theory is, and works very well for classic shear instabilities. Now the question is, yeah.
Independent of the dimension, right?
Independent of the dimension, yes. This will be true independent of the dimension. But normal mode theory does not work well for boundary layer flows. You have the bypass transition. For shear instability, it works just fine. Means it will just predict the right wave number of the maximum growth. And exactly if you even perturb it with random noise, you will get the right wave number also, and the right exponential growth rate in the initial time. The growth rate will keep on changing after some time because nonlinearity will kick on, but this equation works perfect for shear instabilities. Okay. Now the question is, okay, that's a beautiful mathematical equation. I throw in the velocity profile, I throw in the density profile. It's telling me why that which wave number has the maximum growth. Okay, and what is the growth rate, what speed with which that wave will move. Everything it is telling us. Now the question is, what is actually happening? Like if I'm as a physicist wearing a physicist's hat, I'll be very interested to know why I'm having instability in the first place. Like why these wave numbers are suddenly growing, and like what's actually physically happening. So let's take this classic problem where I have I have a fluid which is layered like this. Layered flow, and as you know, it is gravitationally stable. Heavy fluid, lighter fluid, or whatever, it's gravitationally stable. Also, it is also easy to prove that this thing, if you have a constant velocity shear like this, it is also stable. It is also stable. So there is a theorem called Rayleigh's theorem, and also there is called the Fischer-Tropsch's theorem. These are classic theorems in hydrodynamic stability that says that this thing is stable, and that is true to normal mode instabilities. Okay. Now, if you have both, you should expect that the thing will be doubly stable, because you have stability, But it turns out that it is exponential, it is unstable. Not only it has exponential growth, and the structures look like this. So now the question is, I am not making any physical sense of of the equations which were there. I can put in that, I can put in that. Physically, it seems to be stable, and we get an instability. So the question, so G.I. Taylor, this is a very famous quote, I would say, that it is simple matter to work out the equations which must be satisfied by waves in such a fluid, but the interpretation of solutions of these equations is a matter of considerable difficulty. So along these lines, I'll move, like I'll try to explain, why this kind of configuration can be unstable, and there is a physical reason behind it. So we will be looking for physical reason behind instability. So this is, I'll say, the non-traditional approach to stratified shear instability, and it is kind of an intuitive explanation of it. So this is, they say, the resonant wave interaction. So it was, so most of, some of these things were actually proposed by Taylor or Holmboe. These are some big guys, but these were, like, there were no mathematical description that these were mostly hypotheses. So it is like this. So if you have a fluid, you are putting in some waves. You are disturbing it with waves of different wave numbers. Now what can happen is that two waves can lock in phase. So that happens at some point t0 after start, and once they lock in phase, they keep on growing exponentially in amplitude. So it is called phase locking and then mutual growth. Okay. So what I'll be doing, so the theory, so the hypothesis is, so this is the blue area which I will say that people have looked into. So people have, there were some literature where said that, as I said, maybe Taylor said that this is going to happen. So, but they always started with an initial condition that exactly starts from here. But what I want to do is, I am not doing any kind of, I start with any general initial condition. I have no bias. I just start with any initial condition, and from that I see whether any two waves lock in phase and resonate. So I do not start, so what I'm trying to say is that if there is some literature existing, they start from here. I'm starting here where the two waves are actually interacting, and they may or may not lock in phase. I have no a priori information that they are going to lock in phase. That is, whatever happens after t0, that's a hypothesis that might lock in phase, but we will see eventually what happens. And also, as I'm talking about waves, I have never mentioned what kind of waves. So when people do GFD, they talk about gravity waves, Rossby waves, the gravity Rossby waves, Yanai, also known as Yanai waves, so Poincare waves. I'm not talking about any particular wave because the theory is so general that it can work on any kind of wave you give. So let's move to this thing which I call the wave interaction theory. You have question? Oh no. So what I'm trying to say is that forget about this part in red. This thing, as you can recall, this is the simplest thing in fluid mechanics. So the very first principle, this is called the kinematic condition. It basically says that a particle on an interface will stay there forever. It is just so general that it is applicable to any kind of an interface, provided the interface is non-diffusive. Then you cannot actually define a parcel on the interface. But kinematic condition on the surface of water surface, any surface, any interface, you can define a kinematic condition. Now the interesting thing is that what I'm looking at, if there are multiple interfaces, then how these two interfaces talk to each other. Okay, and they talk to each other through this. So this is interface 1, and this is the vertical velocity at the interface 1, but there is an effect of the vertical velocity of interface 2. So what I'm trying to say is that the vertical velocity at interface 2 is, at this position, is this big black arrow. This keeps on exponentially decaying, has a small effect on the top wave. Similarly, this guy has an effect on the second wave. So these two waves, if the distance between the two waves is huge, they are never going to talk to each other. But if the waves are very close, they are going to talk to each other. And that gives actually the length scale for shear instabilities. Like why you have some long waves which are unstable, but short waves which are stable, and that actually comes from what the distance between the two interfaces. So these two interfaces are actually talking to each other. And now what I do not put the normal mode form. I put something very general. More general. I won't say very general, but it is definitely more general than that. I don't have an exponential dependence on time. I have a general dependence on time. This is a real number. This is a real number. And then e to the power I alpha x is fine. It is has a wave number of alpha, but the phase is not alpha ct, but some general phase. I just keep it like this. Now, I have the similar type of thing on w, because my variables are eta and w, and I substitute here. And what I get are 4 equations. So these are 2 waves. Maybe its amplitude at some time is a eta 1, a eta 2. I define a variable r, which is the amplitude ratio, and a variable phi, which is the difference in phases between the two. Okay. So what it is, and these are the velocities at the interfaces. Now, on substitution on these equations, we get these 4 equations. This is the growth rate of the first wave, the phase speed of the first wave, the growth rate of the second wave, and the phase speed of the second wave. Okay. Now going to the first equation, what this red thing tells us is, so the red means, see, it is omega 2, which is some frequency of the second wave. So this guy tells us that if there is no second wave, the first wave will never grow. A wave cannot grow on its own. A wave needs to extract energy from, yes. Huh? Which one? This one? No, it is fine. Which one? No, u1 and u2 could be, it is a general velocity. It could be just any velocity. I am not saying that. No, that does not. No, you can put negative. That doesn't. It's just an advection. It's just the advection equation, right? It does not matter. Huh? Yes. These all of my these things are definitely real. All are real. Yes. Yeah. So what the thing is, I have the growth rate and phase speed. So what I'm trying to say is that if 2 waves are not present, this wave will never grow because this part will be absent. Similarly, for that, it will be absent. And similarly, the phase speeds, if you see, forget about u1 and u2 for the moment because it is the Doppler shift. Phase speed is omega by alpha. Phase speed is omega. So alpha is a wave number, omega is a frequency. So phase speed is omega by alpha, but that changes because of the effect of the second wave. So these 2 waves are changing each other's phase speed and changing each other's growth rate. Okay. So now at this point, see, these used to be PDEs, now they are ODEs, and now what I do is I subtract this equation from that, this like equation 1 from equation 3, and similarly equation 2 from equation 4. What I get are this set of equations, and it is a dynamical, autonomous, nonlinear dynamical system. So somehow I move from the wave theory towards a dynamical system theory. Okay, and what I will be first looking at is the equilibrium points. That's the first thing to do, look at the equilibrium points. And we have 2 equilibrium, we have this equilibrium point given by that and this. And
Sorry, Anirban, maybe I missed it.
Yeah.
But when you're writing down these set of coupled equations for the moment, you don't have to worry about Boussinesq, Navier Stokes.
For these ones, no.
I mean, you don't see that coming in.
Yes, it just
You just need to to worry about the affection at the time that...
Yes, it is so general. Yeah, it is just two things. Yeah, very good question. These are just, this does not, it just cares about few things. Yeah, it does not care about any such thing. It's kinematic condition. Yeah, that's nearly two-dimension kinematic condition.
So these are linear, but you ended up with non-linear.
Yeah, that's also a very good question, because these are linearized material derivatives. These are linear equations, but these are nonlinear. This is a nonlinear dynamical system. This is a nonlinear dynamical system, on which we are actually working on right now. So, but this is a two-dimensional system, so there is no chance of having chaos. But this is a nonlinear dynamical system, which is a very important point for our research right now. So again, what I'm trying to say is that we have this equilibrium point where this is cos inverse something, and cos inverse something would imply that this guy has to be less than 1, less than equal to 1, which is the reason for existence of the equilibrium point. Otherwise, the equilibrium point wouldn't exist. And now the question is, what is the meaning of equilibrium point in this case? So this is showing just a video of two waves interacting with each other. The top wave is moving to the left, the bottom wave is moving to the right, interacting. Now the interaction keeps on, they are almost phase locking, and now they are completely phase locked. And now you won't see much changes. Yeah, it's almost phase locked. So this is actually what is happening. The mathematics was there, but it is what you see is this thing. So the equilibrium point, if for some wave number, so the equilibrium points are, if you just have the phase portrait, it will just tell you that you have a source and sink type system. It's a very simple dynamical system, and maybe you start with somewhere here. So the two waves maybe initially has this phase difference, and maybe this is the amplitude ratio, and they will always end up here.
This is of that coupled system you had, the nonlinear system.
The nonlinear system, yes, exactly. They will end up here. And so from the phase portrait, you can understand that wherever even you start, except at this point, you will always end up you will always end up here, and that's precisely what is showing here, that you start with any phase difference, any initial phase difference, and any initial amplitude ratio. Whatever you start, you end up somewhere. You end up at a steady state. It need not be 1. It is a special case which I am showing here, but it need not be 1. Okay. Huh? Two interfaces, and the fluid extends to infinity maybe. So you have just two interfaces. You can think of it to be two density interfaces, and yeah, it's like this. This is the interface 1, interface 2. Yes, and it does not care about anything. What I'm just putting a density. It could be a vorticity interface also. Just any interface, fluid interface will work. Okay. So this is by equilibrium point, I will mean dr dt equals to 0. Dr dt equals to 0 means gamma 1 equals to gamma 2. Two waves, both the waves have the same growth rate. That basically means and also it can be shown that that's the exponential growth. So this is actually what happens in normal mode. Normal modes grow exponentially, and all the waves will grow at the same rate, e to the power gamma t. Similarly, d phi dt equals to 0, phase locking means the waves have the same phase speed, which means that the waves are phase locked. So the equilibrium d phi dt equals to 0, so it means that dynamical systems, what we are calling equilibrium points, in wave theory it means resonance because C1 equals to C2, and furthermore, in linear stability theory, they mean normal modes. So these three are the same thing in this case. So it's just that you are figuring it out. One is a wave. You are looking at it in a normal mode perspective. You are looking at it in terms of equilibrium points or fixed points. So this is just, I wanted to show that not everything will converge to that. Means it depends on the wave number. Like everything, if everything is convergent, then everything will grow exponentially, and the world is not so unstable. So there are wave numbers for which it does not, definitely there are no equilibrium points, and that is something, the phase portrait would look like this. And
sorry, physically what does it mean when you don't have a fixed point?
the waves will keep on interacting, but they will never lock in phase.
So then the growth rates are negative?
No, the growth rates could be, it's the case of transient growth. They could have some growth rate, some algebraic growth rate. So the time is nearly.
Have an exponential probably in the
Yes, they will.
the real part of
Yeah, they may feel each other, but not much. So can I have just 2 minutes or 2, 3? Okay.
and then we'll see about this.
3. So what I had this thing, the criteria. So this is basically what I'm trying to say is is a necessary and sufficient condition for shear instabilities to occur. Because if this condition is satisfied, you get the phase locking, and that's the thing. So I never mentioned the wave types, but you throw in different types of waves. You throw in, so this is the classic Rayleigh shear layer. Okay, very textbook. You throw in 2 vorticity waves, you get exactly, you give it in this equation, you have the omega, in that case omega 1 is half, omega 2 is half, u1 is 1, u2 is -1, and z1 minus z2 is 2. You just plug it in, you will get this bound, and that is actually the bound you will get. So yeah, in Rayleigh shear layer, you have vorticity interfaces. So Rayleigh shear layer, if you do a classic textbook, you take the Rayleigh's equation and you do it, you get this is the range. The equation I showed, you plug it in, you'll again get you'll verify your answer, that this is the answer. So now you change it. This is the problem I was showing. You have a linear shear and 2 density jumps, so these 2 waves will phase lock. And if you put them as gravity waves, you'll get this new criterion. Again, I said my omega is general. You just put it in and you will get the right bounds. Similarly, you get for the another case, the Holmboe instability. But I'll just like to show with oscillators. So coupled oscillators have the very similar physics. So just to complete, so 2 oscillators, they are interacting with each other because of this on the stuff on which they are sitting, and you'll see that they are not in sync now, but now you'll see that they are making this. They have locked in phase, exactly similar, very similar to how you see the locking in phase of the wave. And why it's not? So recall the phase portrait. We have source and sink like this. So sink is the antiphase normal mode when they are like that, and in phase normal mode, and antiphase normal mode is the source. So basically what I'm trying to, just to finish it, and the equations are actually very similar of coupled oscillators, and what I get in my equations are actually very, very similar. So I'll summarize by wave interaction theory actually provides a physical understanding of shear instabilities, and I have an necessary and sufficient condition for idealized cases. There were many maths and there were maths in the board too, which I didn't get time to explain, but that's fine. And the initial time when they are actually not before phase locking, whatever is happening, is something very interesting. Now in shear instability or hydrodynamic instabilities, it is called transient growth mechanisms, and it brings normal mode theory, wave theory, and dynamical systems under one umbrella. So that's where I should end. I've gone way beyond time. Okay.
Just try to understand. I mean, so basically you've written down these phenomenological equations, and that's what your analysis is based on, right?
Right.
So I mean, could you not have predicted from those phenomenological equations that you're going to have either stable fixed points or unstable fixed points?
No,
it's sort of where is the fluid part of it coming in?
The fluid part is only coming in when you define where the fluid part is.
Define the waves, basically.
No, waves, and the fluid part is also in the kinematic condition.
Kinematic condition, okay.
The kinematic condition is the basic fluid part. Okay. So that's.
Then you don't probably need to worry about anything like Boussinesq.
No, I do not. Exactly.
Understand why
The Boussinesq or everything will come when you. I mentioned about this to be a gravity wave, interfacial gravity wave. That is a Boussinesq. So that's when in this case I have done a Boussinesq approximation, but it is not important. It will work even for non-Boussinesq cases. Right.
Some kinematic to come down later. Then you stay with this.
Right, right. So it is what you're so what happens is that the two waves interact, they try to move to the sink. Now they are phase locked. After that it goes on growing exponentially. Finds link with synchronization theory, a universal concept in nonlinear sciences. So I don't understand by what do you mean by stable? Because if you have an anti-phase, if you draw the phase portrait, you will get a phase portrait like this. And if you draw the phase portrait of this, when they are like that, you will get a sync type of a system in the dynamic. If you
slightly different from anti-phase, you won't relax to the anti-phase.
From the phase portrait, you can think about it as an equilibrium.
Right.
Yes.
Yes. There you will. So for that, he's drawn these arrows. So if you just go outside, you'll get fall time.
Yes. Yes.
Yeah, that's it.
Just a phase portrait will tell you. These are very simple equations are there. You'll just for these two. There are two modes, right? One will have two modes. One is the in phase mode, and the other is the anti phase mode. One is source, the other is sink. That's it. What interface? Kinematic, the interface that is in the fluid dynamics part. So it is a relation from fluid dynamics to oscillator synchronization. So now at this point the interface thing it is lost. It is in the fluid dynamics part. Okay, if you are doing it with that instabilities, it is there. Okay, but in the two oscillators you do not have an interface. It's just that they have a mathematical similarity which I am trying to draw. Okay.
There is a quick question.
Yeah, I have finished the three interface problem. That gives you to chaotic results. Yes. So three oscillator problem is a classic. I think N oscillator, Kuramoto problem. These are things.
So we can talk later.
These are Pikovsky's book has all of those things.
We discuss it.
So, in spite of Pastor rushing me, are there any other questions? Someone? Okay, people. Yeah. Sorry, quick one.
Normally without the red term. Sorry. The red term is that like ad hoc? I mean, I understand.
No, not ad hoc.
Because it should violate something, right?
No, it is not violating. It is these equations which I do not have time. I can go through it. Okay. It is simple. The only thing is that your velocity profile has to be piecewise continuous. That is the only thing which has to, or it is only for applicable to piecewise profiles, not to general like continuous profiles. Otherwise, you cannot define an interface. You have to be able to define an interface. Whenever you define it, it works. Huh?
Could you consider the critical layer?
Critical layer is, yes, we have submitted one in JFM with critical layer inside. Yes, you can also. Critical layer is also an interface in some sense, so you can also do that. Okay.
Very good. So let's send the speaker once again.